Hi students, so we'll study magnetic effects of current. This is a part 4. Already I made part 1, part 2, part 3. So please watch that part 3 parts now and come back to this 4th part so that you can understand very clearly, right? So in this 4th part we'll study force acting on one current carrying conductor. If a current carrying conductor is placed in a external magnetic field, so it is going to experience a force. So how much force is going to experience now, that we are going to discuss in this one now, right? Or we can call it as like a motor effect, how the motor is running now. So it is based on this principle only, right? So therefore force acting on current carrying conductor placed in external magnetic field, right? This is one current carrying conductor is there. So therefore one current carrying conductor placed in an external magnetic field. So what will happen now? Suppose there is one magnetic field is there now, okay? Suppose there is some magnetic field is there. This is one magnetic field. You know already, if you see the part 1 or part 2, even moving charges, no, I discussed this magnetic field. This is a uniform magnetic field. So the magnetic field direction is into this board. Clear? So therefore here one small current carrying conductor we are placing here now, suppose, right? So one current carrying conductor we are placing. So this current carrying conductor, no. So here this current is flowing here now. Current is flowing is I. Now will it is experience a force or not? Yes. How? See, current is flowing now. Current is flowing means what will happen now? That means charges are moving. That means electrons are moving in this direction. That means positive charges are going in this direction. We can assume. So this is your a current is nothing but a flow of charges now. The charges are flowing into this one now. So the charges will experience a force like that. Therefore the current is there, wire is there, no, it will be also able to experience a force now. Suppose this is your direction of your charges, no, positive charges. So this side it will be your magnetic field and this side it will be your force. So therefore the force acting on this one it will be F. That is, we already studied Fleming's left hand rule. So this is what you have to do, no, central finger indicate the direction of the current or direction of the positive charges now. This first finger indicate the field. This thumb indicate the motion in which direction is going to move. So this is the current now, current is there, magnetic field is into the board, so it is going to experience a force here now. Suppose the current is flowing toward this direction, magnetic field here downward. That means if you change the direction of the current, so force direction is also will change. So we want to calculate how much force is acting on this one now. So clearly try to understand this, very important no, right? So in moving charges, no, we already discussed force experienced by the charge, right, placed in a magnetic field, no, we already studied Q into, so V cross B, clear? So therefore V is nothing but a velocity, clear? So now we can rewrite it as velocity of the charges now. Velocity of the charges are, velocity, with what velocity the charges are flowing. Velocity means what you can write it now, we can take it as one small element dl. Right. So this small element is crossing it in time t dt. So therefore we can rewrite it as F is equals to a small element we are taking now df. Clear? So it is Q into dl by therefore dt cross b vector. So what I can write it now, dl. Therefore here I am taking here now. So this is small amount of charge dq. So therefore dq by dt is nothing but a df is equals to current into dl cross b. So if you do the integration of this one, so here one interesting formula you will get it now, df. So df will become like a f now. So f in is equals to current into integral dl. Integral dl means what? The total small elements, no, small elements, no, vectorially we have to add it. Vectorially. So vectorially we can add it now. Therefore length is L cross B. Therefore calculating of the length, no, is very important, no. See here, most of the students, suppose if your wire, straight wire is there, you can take the length is now. But if it is like a one circular wire is there, no, coil, no. So you should not take like a pi r onto this one, no, because these small elements, no, if you are added, no, so it will become like a effective distance, like our triangle of addition of vectors, no, we can get it as the shortest distance between these 2 points. So we can take it as like a L, not this one, no. Clear? Huh? So one more time we will discuss about this one, no. So we will see about the length. So now what I got it now, force experienced by current carrying conductor F is equals to I into L cross B. So how to calculate this force direction? Again you can use same thing, therefore Fleming's left hand rule. There are 3 to 4 rules also is there, no, to identify the direction, no, but we'll go for best one, no, very easy. So that is nothing but a Fleming's left hand rule. So what we are doing now, therefore left hand you have to take it now, left hand, stretch these 3 fingers. How 3 fingers are to be stretched? So mutually perpendicular to each other. There is x axis, y axis, z axis, like that. Correct? So therefore here, no, so this is central finger indicate the direction of the current. This is indicate the direction of your field. This is direction of your force. Here suppose here again you can see this is a current, no. So this side, inside is the field, inside is the field. So this side it will be your force. You understand? And this force, L cross B, cross product, if you are anytime if you see it, no. So force will be always perpendicular to the length and force will be always perpendicular to the magnetic field. Perpendicularity condition means what you can write, F dot L, it will be equal to 0. That is F dot B, it will be also equal to 0. Clear? Force will be always perpendicular to length of this one, no, and also force will be perpendicular to magnetic field, right? Again one more small concept we can rewrite it as, therefore F is equals to I into therefore L cross B. Now so we can rewrite it as, therefore L cross B I can rewrite it as, so I into L cross B is nothing but L into B into sin theta. This is your force. Therefore in this force, therefore what you can rewrite it now, right? So here force will be maximum force when you will get it now, that is nothing but a B into I into L. Yes, so therefore sin theta, therefore it will be equal to 1. This is only the maximum now, that is nothing but a theta is equals to 90 degree. Clear? So theta is equals to 90 degree, sin 90 is nothing but a 1. Similarly when the force will be the 0 here now, when the force will be the 0, if current is not flowing, that means current is 0. That means if it is non-flowing current is there, no, if it is placed inside the magnetic field, it will never experience a magnetic field, no. And also if it is effective length of this one, no, is also 0. That means a complete closed circular coil is there, no. So therefore that also will not experience any force, no. It will expand and it will comes to rest onto this, right? So it will not experience any force, no. And if there is no external magnetic field, if magnetic field is not there, also force will be 0. And also sin theta, therefore sin theta is equals to 0. That means theta is equals to 0 degree or theta is equals to 180 degree. That means, so if suppose there is a magnetic field is there, suppose here there is a magnetic field is there, no, it is like this. So it is like this. How the magnetic field? It is into the board. So if a current carrying conductor is placed along the magnetic field, so it will not experience any force. If a current carrying conductor is opposite to the magnetic field, no, therefore it will not experience any force, right? Clear, no? So therefore if a current carrying conductor is along the direction of your magnetic field, force will be 0, or opposite to the direction of your magnetic field, force will be 0. So if a wire is there perpendicular to the magnetic field, therefore force will be maximum. Okay, so keep in mind. So this one, no. So one more interesting, one small concept, no. Suppose here there will be one magnetic field is there, no. This magnetic field, suppose here. So this clarity should be there here, no. Suppose here there is a one coil is there, no. This is one coil, no. Therefore one current carrying conductor is there like this. So what you are going to take it now, length of this one, no, this is your current, no. So what you are going to take the length now, this length you should not take it as this one, no. So total effect, right, you have to take it as like a effective length, the shortest distance only. This is only you have to take it as length is L. Clear? So how it is making an angle also you can calculate it now. Then you have to take it as F is equals to I into L into B into sin theta. What is L here now? L is nothing but this distance, not actual length of this one now. Clear? So this is one confusion now. So can you tell me one small question here now? Simple question. So this is a magnetic field here then. So this is a magnetic field. Now a current carrying conductor is there here now. The current carrying conductor, how it is there now? The current carrying conductor is like this. This is a current. Correct? So is the radius is R. Therefore is the radius is R. So what will be the magnetic field here now? Magnetic field is B. So what will be the force here now? Force is nothing but a B into magnetic field is I into L into. So therefore here it is this is L. So L is what? This length is equals to therefore 2R. Therefore sin 90. So F is equals to what will be the F now? Therefore F is equals to so B into I into 2R. So this is the force which is acting on this. Clear? Okay students, right? So some more applications no we'll discuss in the next part of this one. No? In this fifth part no we'll study so force between the two parallel current carrying conductors now, right? Force between two parallel current carrying conductors. Force between two parallel current carrying conductors, right? So what will be the force now? Just now we discussed force on a current carrying conductor placed in a magnetic field. We studied no. Therefore B into I into L into sin theta. This is the force experienced by the current carrying conductor placed in an external magnetic field. This we studied in a fourth part now. Please go through it, fourth part, then come back to the fifth part so that you can understand very clearly. So now let us see, this also very important question even for board examination also. Let us see. Now I will take two parallel current carrying conductors. See, this is your current I1 and this is one more current carrying conductor is I2. These two are infinitely long current carrying conductors are there. These are infinitely long. These two are separated by distances D. Now we want to calculate what will be the force between these two wires now. Now here, now let us calculate now force on this one. First of all, there is no external magnetic field to apply this force no. So, but you try to see this one current carrying conductor is there no. This current carrying conductor creating a magnetic field. How it is creating the magnetic field now? You have to use right hand thumb rule, right? Don't use maximum number of rules to find the direction. Stick on to one or two. That's all, right? So here this is one current carrying conductor. So this current, right hand thumb rule, current, magnetic field. The magnetic field is created. How the magnetic field is created now? The magnetic field is created like this. So therefore in this way the magnetic field is created. What will be the magnetic field now? This B1. So this we studied in a second part. Please try to go through this one now. So the magnetic field due to the current carrying conductor infinitely long. What is the formula? That is nothing but a mu naught I by therefore 2 pi into D. This is here. This is I1 because I1 is the current. Now how the magnetic field is there now? So therefore it is into this. Therefore, so here now the magnetic field is there, current carrying conductor is there. So therefore here now you get this wire will be experiencing a force. What is this one now? You have to use Fleming's left hand rule. So this is your left hand, right? So central finger indicate the direction of your current. This one is the direction of your field. This side it will be a force. Therefore this is experience a force. This is force on the second one now, right? So how it is going to experience a force now? What is the formula? Same formula. Force on the second one now. So due to first one now, it will be equal to B1 into I2 into length of the some part of this. B1 because B1 is a magnetic field. Current, this is I2. So substitute here now, what you will get it now? Mu naught I1 I2 by 2 pi D into length of the part, full part not, therefore some part of the length is going to experience a force. This is F2. So this is a force experienced by this current carrying conductor in which direction? Toward this direction. So similarly, this wire also experience a force no. How? because upon this one, no, therefore here this magnetic field, so this current carrying conductor producing a magnetic field at this point. How? Therefore here this is a current, no, therefore here the magnetic field will be there. This is outward, right? How the outward is there now? Therefore in this way the magnetic field is created now. Clear? So magnetic field is created in this way, right? So magnetic field is created now. So in which direction? Therefore it is B2. So B2 is nothing but a mu naught into I2 by 2 pi into D. So this is a magnetic field in which direction? Outward. Now Fleming's left hand rule. So this is a current. So this side it will be outward, right? So this is a current outward. This side it will be a force. Therefore it is going to experience a force toward this side. This is F1, right? So how to calculate? Again you will get the same formula here, no? So you try to do substitute it, no? You can get your answer now, right? Same formula you are going to get it. That is what is the same, right? So force on the one, that is nothing but a, so magnetic field is B2 and current is I1 into suppose some length of this one. So what you can rewrite it as now? Therefore B2 is how much, no? Mu naught into I2 by 2 pi D into I1 into L. This is F1. Try to observe. So this mu naught by 2 pi, I1 I2 by D, I1 I2 by D, so into length. Therefore, so they are going to experience the same force onto this one, no? So this force, how they are now? This is a parallel current carrying conductors. What will happen now? They are going to attract each other. You are understanding? So this parallel current carrying conductors, no, what will happen now? They will attract each other. Clear? So you can remember one point, no? A parallel current carrying conductors attract each other. With what force now? With what force here? So the force is nothing but a F is equals to mu naught by 2 pi into I1 I2 by D. So force per unit length, no, you can rewrite it as, so mu naught into I1 I2 by D. But here important formula is what? A parallel current carrying conductors, they are going to attract each other, right? So now we want to study therefore anti-parallel current carrying conductors, right? So how I did this one, no? So similarly, what you can write it now? Anti-parallel current carrying conductors. How that anti-parallel current carrying conductors now? So therefore here this is one direction, no? So this is I1 and this side therefore I2. So therefore these are anti-parallel. These are anti-parallel, infinitely long. So what will happen now? Infinitely long. So what will happen now? They are experiencing outward force now. This is outward force. This is, so F2 and this is F1. What is the force here now? Again the same. Therefore now you can rewrite it as anti-parallel current carrying conductors. Anti-parallel current carrying conductors. Anti-parallel current carrying conductors will repel each other. What is the force here now? So what is the force here now? Force it will be equal to F by L is equals to mu naught by 2 pi into I1 into I2 by D. Clear? So now by using this concept now, right? So we can go for, so we'll study the definition of 1 ampere, right? So in general definition, no, we studied that if 1 coulomb of charge is flowing in 1 second, no, therefore it is said to be like 1 ampere. So but really 1 coulomb, right? We don't know that. So we'll see in. Now here by using this one, no, we can define it as, therefore here there is a current is flowing. So therefore here I1 and this is one more current is flowing, maybe parallel or anti-parallel. So this also I2. These two are separated by 1 meter distance. Here 1 ampere current should be flown, so that, okay, so that the force between, they are separated by 1 meter distance. If you substitute here now, what you will get the formula? Force per unit length. Okay, length of this part is also 1 meter. That means, so force is equals to mu naught by 2 pi, so into I1 I2 by D into length, right? So if they are separated by 1 meter distance, mu naught by 2 pi into I1 I2, therefore I1 I2 divided by 1 into length of this one is also 1 meter. So if current flowing between this one is like say to be like 1 ampere, so therefore 1 into 1, what you can write it now, mu naught by 2 pi into 1 into 1 is 1 now. So the force between them may be attraction force or may be repulsion force, no, force between them should be equal to the force between them mu naught by 2 pi, means mu naught value is how much now, 4 pi into 10 to the power of minus 7 by 2 pi. So what you will get it now, therefore 2 into 10 to the power of minus 7. So if a current carrying conductors are there, so they are separated by distance 1 meter, so that the one current carrying through this one is said to be 1 ampere if the force between the wires is said to be or experience said to be force is equals to 2 into 10 to the power of minus 7 per Newton per meter. That means, so this much amount of force should experience for 1 meter length of the wire. Clear? So in this way the definition of 1 ampere was given, no, which is accepted everywhere, right? So be careful, no, this one. Now we will go for one question related to this. Suppose a current carrying conductors are there. So this is suppose here current it will be equal to 10 ampere. Here therefore one more wire is there, no, this is one wire A and wire B. So therefore it will be 20 ampere current is there, no. Suppose here this is said to be like a toward this side 30 ampere. You can see any different onto this. So suppose here between this one, no, therefore here 10 centimeter, this distance between them is also suppose 10 centimeter. Now like these wires are there, no, so length of this part, okay, length of it is said to be like a 1 meter part of the 1 meter part of the wire, right? So we want to calculate what will be the force acting on this wire, force acting on this wire or force acting on this wire, right? Force acting on A, force acting on B and force acting on C now, right? So what is the force acting on A? So I'll do one or two questions, no, you try to do remaining part, no. Force acting on A, in A, right? Let us see. So you try to say what is the force acting on A is because of due to B, because of due to C. Now you see the parallel current carrying conductors, these two are parallel force because of due to B. So because of due to this one, no, parallel current carrying conductors, no, what will happen now? So they will attract each other. So attract means because of due to this B, so what will happen now? It is going to experience a force, that is force due to B. And due to C they are said to be anti-parallel. So anti-parallel, therefore 30 ampere, no. So anti-parallel, what will happen now here? So these two are going to repel each other, no, therefore force acting on A is because of due to C is it is outward. Clear? So how they are acting now? They are acting in the opposite direction now. So which force will be more? Either force of B or force of C. If force B is more, this wire will be able to experience a force toward this side. Force of C is greater, means it will be outward. Right. So now we'll calculate force on B, then force on C, then we'll see which one is greater. Then both are acting in opposite direction. We will subtract it now. First let us calculate force due to B. How much now force due to B now? What is the formula? Right? We written. What is the formula? Mu naught by 2 pi into currents because of due to this one, no, 10 into 20 divided by distance is how much now? 10 into 10 the power of minus 2 into 1. Clear? 1 meter. How much it will be? This 10 cancel here, no. So this also it is okay. So will not cancel this one, no. So now we'll write down mu naught by 2 pi into taken here, no, therefore 2000, correct. So this is force due to B. Now let us see force due to C. Now we'll see force due to C part. How much it will be now? Again mu naught by 2 pi into due to C means because of due to this one. So this is 10 into how much distance it is there? What is the current here now? 30 ampere. Distance how much now? 20 into 10 the power of minus 2 into 1. Clear? So now how much it will be? Here these two get cancelled out. Okay. Now so here 2 it will be 5, right? So 5 3 is 15. So therefore mu naught by 2 pi into 1500. So due to C. Tell me now, mu naught by 2 pi, mu naught by 2 pi. Same. Here 2000 is there, here 1500 is there. Which is greater now? So 2000 is greater, that means this is greater. So the total force acting on this one is toward this side, force on A. So therefore dominating force was what? Force on B minus force due to C now. So it is how much now? Mu naught by 2 pi taken common now. 2000 minus 1500. So therefore mu naught by, therefore 2 pi into 500. Right? How I got 500? 2000 minus 1500. Clear? So therefore mu naught by 2 pi how much now? 2 into 10 the power of minus 7 into 5000 and 500. 500 means 1000 means 10 the power of minus 3. So 10 the power of 3, 10 the power of minus 7, therefore 10 the power of minus 4 newtons. This is the force acting on A. Towards which side? On this side. Similarly, you can calculate force on B and force on C. Like this we can calculate it now, and we can solve the problems now, right? So I will teach you. Therefore force on B you try to do, and force on C now. Therefore I will do force on this B. Now you try to observe, these are the two parallel current carrying conductors. Parallel means what? So they are going to attract each other. That means this will be experience a force toward this side. Correct? So force on this one is how much now? So due to this A, and this is anti-parallel. Anti-parallel means what will happen now? They are going to repel each other. So this side it will be F due to C. Both the forces are acting in the same direction. No need to check whether it is in which direction it will move. Both the forces are acting in one direction only. So it should be acting in the left side. Therefore force on B we can add directly force due to A and force due to C. Right? Force due to A is how much now? A mu naught by, therefore 2 pi into I1 I2, therefore 10 into 20 divided by the distance between them is how much now? 10 into 10 the power of minus 2 plus, and force due to C, due to this C, so mu naught by 2 pi into the product of the currents, therefore 20 into 30. So distance between them is 10 centimeter, 10 into 10 the power of minus 2. So into 1, actually into 1 is length of this part. So this 10 cancel here now, this 0 cancel here now. How much it will be? So this is mu naught by 2 pi into, so this taken here now, 2000 plus mu naught by 2 pi into taken here now, therefore 60. So 60 therefore into 2, 6000. So 6000 plus this one, no, that is nothing but 8000. Mu naught by 2 pi into 8000. So how much it will be now? Now, so here mu naught by 2 pi, 2 into 10 the power of minus 7 into 8000. So 16,000 into 10 the power of minus 7. So therefore 16 into 10 the power of minus 4 newtons towards left. This is towards right. Clear? Like this you can calculate the force acting on this another wire now.